Okay, so hello, I'm Chris. Good morning, good evening, and good night, wherever you are in the world. And this is my entry in the student research competition. So let's begin by, one second. Yeah, let's begin by a motivating example for the problem that we have. So take this function right here and pretend that we want to, for some reason, find a minimum using gradient descent or something like that. So using the derivative, we can descend down the left side of this function. We can go, and then we can go, and then we can go, and then we can stop. And unfortunately, when the derivative here from the left-hand side is 0. So the function, for all intents and purposes, the information that we get from this function, from the derivative of this function, tells us that there's no further left to go at this point. Unfortunately, there's this lower point down here, and the derivative the traditional derivative does not capture this information. Furthermore, if you can see this this function on the left here, this is just an if statement. So we can model this kind of jump discontinuity where the information is not captured by the derivative just using conditionals. And so we're in a little bit of a pickle here because conditionals are useful and we like to be able to take the derivatives of things for things like gradient descent. And so we need to offer a solution, come to a solution. The solution that we offer is from distribution theory. And so in order for distribution theory to make any sense at all, we need to go through test functions first. Test functions are a set of functions that have some very nice properties that we want. First of all, they are infinitely differentiable. This is non-negotiable. The space of test functions have the property that they're infinitely differentiable. They have complex support, meaning that they are 0 except for a small enclosable area. So we should be able to draw a circle around the area that that test functions are non-zero. I'll show a picture of that in a moment. For notational sanity, we'll just denote the space of test functions phi, because we'll want to note the type domains of functions later. And they look kind of like this function here. So there's 0 for a long time, and then there's a bump. And so they can be shifted left and right, and they can be made thinner and taller. So they can be made arbitrarily skinny and arbitrarily tall. So now we can get to distributions. Distributions are kind of a theory of generalized functions, and I'll explain what I mean by that in a second. So they're continuous linear functionals, which if you don't have an analysis background, won't make a great deal of sense to you, but we'll give an intuitive sense of them in a moment. There's a canonical mapping from every locally integrable function from Rm to R to a distribution. So we can take any locally integrable function, so this includes any piecewise differentiable function, and we can map it to a distribution using the test map on screen. And it has the typing, so it has this typing. So it takes a test function and it spits you back a real number. And you can kind of intuitively think about it as taking the average of the points where the test function is non-zero, taking those same points on the underlying function that we've lifted to using the test map, and then taking the average of those values. And the important thing about these is that all of these distributions are infinitely differentiable. On screen, you see the identity for the test map, taking the derivative of the test map. This can be proved pretty easily via integration by parts, but this is just a special case. There are distributions that do not arise from the test map, and those are all infinitely differentiable as well. And so this is what it looks. If we wanted to sample from a distribution using test, if we lifted this using the test map and we wanted to sample from it around the discontinuity, we would integrate it together with this test function, which would give us a rated average of this function around this point, if that makes any sense. And so now we're going to go on to a couple more things that we'll need to go through for another example. So this is the characteristic function. It's just 1 if B, the conditional, is fulfilled, and 0 otherwise. And now we have the direct delta distribution. The direct delta distribution is basically to a point, and we'll spit back the value of the test function at that point. It's relatively self-explanatory. The definitions are up here, so we'll move on from that pretty quickly. So now let's go through a concrete example of differentiating a distribution, which will hopefully be illuminated. So we'll take this function as we had before using the conditional, and we'll model it using the characteristic function, which is the construct that we have in our language. So we have this, and then we lift it. Suppose we lift it to a distribution, and then we take the derivative. We end up with this expression down here, where we differentiate the two branches, and then we add a Dirac delta distribution right in the middle, right where there's a jump discontinuity, and then we multiply that Dirac delta distribution by the magnitude of the discontinuity. So in this case, magnitude is -1, so we multiply the Dirac delta by -1. And this generalizes to functions with arbitrary numbers of discontinuities. You can just keep on adding Dirac deltas and keep on taking branches. And so if we wanted to take the derivative at this point again, where before it was 0 and no rate of change was captured, now we have -1.839, which shows that there is a decrease after that point. So now we do capture that rate of change. So now we just have a little bit of comparison between the two types of derivatives that we have. So traditional derivatives, they're relatively easy, and we can do automatic differentiation. In fact, automatic differentiation was developed around traditional derivatives. You can't differentiate around jump discontinuities. Whereas with distributional derivatives, you can no longer really sample at points, unfortunately, because that's the trade-off that we have with derivatives. But you can sample around arbitrarily small neighborhoods by just shrinking the radius of the test function. Automatic differentiation also becomes hard. Nielsen, Henrik, and ICFP 2003 showed that, or implemented a method of doing automatic differentiation in using distribution theory, but there are limitations, such as there needs to be a finite number of discontinuities, and you needed to know where they are. But the upside is that everything is differentiable, and we'll be able to use that in the next couple in our work. So finally, we get to our work, and unfortunately, there's really no good way of presenting this visually because it's semantics, and it's very difficult to present semantics visually. So here is our type system. We have the first thing that you'll notice is that we have a regular, like our bigger type system for numbers and distributions, and then we have our smaller type system for Booleans, so that we can construct Boolean expressions. And second, you'll notice that we've separated things into tau prime and into tau. This is for two reasons. First of all, we don't want to be able to lift a distribution again, because if you, the test map won't type check if you try and test the distribution. It just doesn't make any sense. And then second of all, we don't want to be able to compare distributions, because that would be like comparing functions. And comparing functions is known to be a hard problem. And so now we'll get into how we dual functions. We dual functions just imperatively. There's nothing particularly new here. It's just that the we just have functions that we can declare with let bindings, and then we stick them into a function environment along with their variables and their terms and the various other things you need to keep track of functions. And then application also isn't really anything new. We just take the arguments and then we substitute them in for what we want. That's just declaration, application. These are nothing new. So now we come to our type system using distributions, or our constructs using distributions. So first we have our lift construct. Our lift construct will take a real valued function, a function from Rn to Rm, and lift it to a distribution using the test map from before. We do this denotationally, but these maps are well defined. We don't particularly need to deal with the algorithm behind them, and until we start having to deal with them operationally. And then the differentiation, construct is defined over distribution. So we can take the derivative of a distribution. So we can lift a function into a distribution, and we take the derivative of that lifted function. And so something important that I should note here is that we have proved that using our language, you can only construct functions with measure zero discontinuities. This means that we can lift or real valued functions with measure zero discontinuities. That means we can lift any function that we can construct and that's real valued from a regular function into a distribution, and then we can take the derivative of that distribution freely. There's no functions that are real valued that would type check that would not be able to be differentiated. And so now we go on to future work. For future work, we do not currently have recursion in this language. And we don't currently have higher order functions. This is something that we're working on. This is difficult because it's hard to deal with denotational semantics around distributions, because complete partial orderings among distributions is kind of a little bit difficult to do. And operational semantics and adequacy is the other thing that we're working on. This is probably harder than recursion higher order semantics, higher order functions, because we would then need to operationally deal with integration, and that is a very, very difficult problem that I'm not sure how to deal with. And all right, thank you very much for your time. And do you have any questions? Here's a picture of my dog.
Thank you, Chris. Is there any question from the audience?
Well, maybe I had a question a bit more about motivation or maybe possible use cases, like what kind of situations would I use this language for?
Oh, yeah, this is kind of a toy language, kind of a proof of concept that we can use distribution theory for things. But the use cases here would be things like, let me go back to the motivating example slide. So with gradient descent, we're trying to minimize a function, right? And the way that we do that is we take the derivative and then we just add that or add that to the point that we're at. We use that to descend the slope. That currently doesn't work if there's a jump discontinuity where there's a 0. So like in this case, if we tried to do that, we would get stuck and be far from the minimum because the minimum is down here. So if we're trying to minimize our function, we wouldn't be able to do that traditionally. Whereas with our yeah, sorry.
Right, so the motivation really comes from like doing mathematics or like finding.
Yeah, something like that.
You have a function, yeah.
Yeah. And for things like machine learning, because gradient descent is a very important machine learning algorithm.
Right, yes. Okay, thanks.
Can you compare your work a little bit with other automatic differentiation techniques? For example, there was a paper at Popple earlier this year by Gordon Plotkin and Martin Nabati. How does that work compare with yours? Are there different trade-offs?
There are some different trade-offs. So ours is harder to do operationally, as I mentioned, because integration is difficult and the test function necessitates it. If I go back over to, and the test map necessitates it. So if I go over back here, the test map necessitates integration with a test function. So that's hard to do. But the trade-off that we get is that we get a better defined notion of differentiation at all points. Because if I remember that paper correctly, and it's been a long time since I've read it, so correct me if I'm wrong, they guarantee differentiability almost everywhere rather than everywhere, whereas we can guarantee differentiability everywhere. I may be thinking of a different paper though, but that's to my understanding what the difference is here, other than the approach that we've used to taking derivatives.
So practically, that means that your technique will be able to handle more programs?
Practically, yeah. It's just more difficult to do and potentially more computationally expensive.
Thank you.
Okay. Any other questions?
I have a question.
Yeah.
Right. So you mentioned that if you switch to distribution theory, that you can no longer sample a point, but rather you have to sample a neighborhood, whether that can be as small as you like.
Yeah.
I'm wondering whether, so I think you suggested that this helps you solve the kind of discontinuity problem.
Yeah.
But I'm wondering whether that prevents something that people usually do. I mean, people have to sample a particular point.
So you can sample to arbitrary precision using this, like within an epsilon neighborhood where epsilon is arbitrarily small. It means that you can't get pointwise data, which could be a problem, though I don't have a particular example of that off of the top of my head, but I can imagine that it might be a problem in some case, that sampling pointwise data may be problematic.
Okay, I see. Thanks, Errol. Thanks a lot.
Okay. If there's no more questions, let's thank Chris again.
All right. Thank you very much.